This standard Cartesian plane maps a simple mathematical parabola. A direct functional relationship maps every y value to a specific x value. As we sweep a vertical line across this curve, it only ever intersects at a single point, guaranteeing a strict one-to-one mathematical relationship. But physical systems rarely follow such neat one-way paths. Celestial bodies and cyclical signals travel in continuous loops. This chart shows an elliptical trajectory. Applying the vertical sweep here, the line strikes the curve in two places at once. Because the path intersects itself, the standard y equals f of x math breaks down completely. It cannot compute the kinematics of a looping path. To accurately model dynamic physical reality, engineers have to abandon the strict vertical relationship between x and y. The solution is to mathematically decouple the spatial dimensions using parametric equations. We express both x and y independently, tethering them to a hidden third variable called the parameter t. By deriving the first and second orders of these new decoupled equations, we can calculate exact spatial kinematics. Mastering parametric calculus allows us to predict system behavior and avoid catastrophic structural errors in engineering design. Our first objective is to find the rate of change of y with respect to x, while keeping that underlying parameter t intact. We use the chain rule to bridge them. We divide the time derivative of y by the time derivative of x. This resolves cleanly into dy over dx, provided the derivative of x with respect to t is not exactly 0. This first derivative allows us to calculate continuous, instantaneous velocity at any point along a self-intersecting trajectory. Calculating velocity is only the first step. To measure spatial acceleration, we need the second derivative, d squared y over dx squared. There is a highly intuitive assumption here that you can simply divide the second-order time derivative of y by the second-order time derivative of x, but this is a mathematical trap that consistently causes severe miscalculations in structural physics. It fails because it completely ignores a crucial nonlinear step-down scaling factor. Because the first derivative remains a function of t, you must apply the chain rule a second time. First, we differentiate our dy over dx output with respect to the parameter t. Then, we multiply the result by the scaling factor dt over dx, which means dividing the entire expression by dx over dt. Omitting this specific scaling factor is the primary root cause of unpredicted physical forces ripping complex systems apart. This is a parametrized circle tracking spatial motion. We map a point moving along its perimeter using a position vector defined by a cosine t and a sine t. Differentiating this position vector component by component generates the velocity vector. This velocity vector maps perfectly tangent to the circular path at all times. Differentiating a second time yields the spatial acceleration vector. The math evaluates to negative a cosine t and negative a sine t, the exact inverse of our position vector. Physically, this vector points dead center, opposite to the outer moving point. This rigorous mathematical relationship is the definitive proof of centripetal acceleration, holding dynamic bodies safely in orbit. We can apply this derived model directly to aerospace dynamics and satellite trajectories. In this environment, we define the parameter t as the orbital epoch, or continuous flight time. The first parametric derivative delivers the instantaneous orbital velocity required for deep space navigation. The second derivative translates into exact gravitational acceleration and spatial g-forces. Solving these precise derivative loads gives structural engineers the data required to prevent spacecraft chassis collapse during complex orbital maneuvers. We apply these exact same principles to the microscale dynamics of reactive alternating current electrical grids. Here, the parameter t is redefined as the electrical time phase, which governs rotating voltage and current phasors. This chart graphs simultaneous AC voltage and current using parametric equations. The result is a geometric figure known as a Lissajous pattern. Calculating the second-order derivative reveals the dynamic stability constraints of capacitive and inductive grid components. Mathematical monitoring of these zones alerts engineering control loops to phase shifts that trigger localized grid failure. Finally, we apply this math to robotics control loops and digital 3D physics engines tracking complex motions. This is a mathematical B-spline curve. The underlying parameter t represents the incremental interpolation step moving along the geometry. The first derivative sets the precise orientational heading of the robotic asset along the path. The second derivative serves a protective function, mathematically guaranteeing c-squared curvature continuity. Enforcing this continuous curvature prevents abrupt velocity jerks, saving mechanical robotic joints from snapping under heavy rotational torque. Today, engineers execute these rules by writing Python scripts that automatically scale the derivatives. Symbolic computational libraries solve the strict math without triggering the scaling trap, while numerical libraries evaluate the physical spatial vectors. Parametric calculus is the required engine for discovering the physical limits of our engineered reality.